So, standard deviation, remind me what I said it was for. Yeah?
It is for, yeah, let's see. So standard deviation is to find the mean distance of each point from the mean.
No, that's what it is rather than what it's for. Yeah.
It's to see if the mean is reliable or not.
Yeah. Explain, Favorite, how it does see whether the mean is reliable or not.
And it's from that.
Mean distance each way. And the mean is considered.
But that's, again, that's sort of what we're doing. But what are we looking at using standard deviation that decides if the mean is reliable? Okay, yeah, so whether the data is dispersed around the mean, okay? Remember I said maybe I could visualize this a bit more today. Right, so I used to use a dartboard analogy, but I don't like that now. Right? So imagine you've got a number line, two number lines, right? And this line represents, in each list, is that vertical?
Yeah.
It's really not,
Yeah.
is it? From an angle, it is, but from where I'm now, right, just listen at the moment. Okay, so imagine this line represents that, which is the
mean.
The mean, thank you. It is said mu, but it represents the mean. So somewhere in the middle. So what did we say? We said, so standard deviation looks at how far all the points away. So let's say I've got data set number 1, and I've got one value that's this side of the mean. Yeah? And I've got another value that's this side of the mean, and another value here, and here, 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 here. Okay, so my data's all spread out. Are you happy enough that looking at all those values, this would be the mean?
Yeah.
Why? It's about in the middle, yeah. That's right. Now, that would be the mean. So if I were to add up the distances, either side, okay, right? They would balance each other out, so the mean would be roughly in the middle. But if I had another set of data and it looked more like this, okay, would that also be the mean?
Yes.
Okay. What you are already you know about, though, is there are different ways to analyze this distribution, isn't there? So we could look at this value and this value compared to this value here. Come on, computer. And this value here. What have I just looked at? So from there to there would be considered the what? The range. Good. Okay. So this distance would be like that. So I can do my analysis, that would be my range, as well as this would be my range. All right? So I've got a mean to represent the data. We know the mean is the same for both. We do know, however, that the range is different, right? So the range shows that this data is more spread. So that's one thing I could look at. All right? But what's the problem with the range? If I said, oh, well, if the range is big, I'm not going to use the mean. But what's the problem with saying that? No thoughts? Well, what if I had a third data line, all right, where the mean is here? I'm going to have the same range as the top one, but this time, so my mean is still in the middle. But this time I'm going to have value there, so the range is the same, but now I'm going to do this. Okay, so you consider these two are potentially outliers, yeah? unless I just start adding in a couple of extra points. Right? But what can you say? Because these might be outliers, we don't know because we've not done the calculation. Is the range a good way of separating this one and this one? No, because you have a lot of compactness in the other data. You just have a couple of values that are spreading out. But that means the range has been affected, right? Make sense? So I can look at the range compared to that one to this one. The middle one makes sense. But actually, what if the data is more spread just with a couple of points? In that case, the range is not going to be a great measure of how the data is distributed. So then we said, right, well, we're going to look at the next thing, which is the standard deviation, right? And what would you know about the standard deviation for the two ones? So, for instance, well, how do we do the standard deviation? Distracted, aren't you? You're not listening. What's the standard deviation basically do? So from the mean to each point, yeah? So measuring the dispersion, but we look at every point, every single one of them. Okay? And we look at how far away it is from the mean, and then what do? We mean it. We find the mean of those distances. And if we look at this one, look, if I try, I can't even draw it because it's not gonna, it's too short. I've got lots of arrows. Come on, you stupid thing. Doesn't want to do it. You get the idea, don't you? Right, for this one, I've got lots of arrows, but they're all very short. So what would the mean distance be for this compared to this one? So this one would have a larger, so this is where we would say the standard deviation is larger. Now that's obvious between those two sets of data, but what about this one and this one? Would they have the same standard deviation, being at the same range, or would the standard deviation be different? So the top one and the bottom one. So 2 is definitely different than the other two, right? Clear. But what about 3 and 1? So again, I think you've already said it. This one has lots of short ones, but it only has a couple of long ones, and then the rest are short. So what would the mean distance be compared to this one? It'd be less than this one, but more than this one. So standard deviation can also then take into consideration data that is quite compact, but only maybe in a couple of points it's a bit larger. Does that make sense? So that's how we're visualizing it. So standard deviation gives us an extra layer of detail to start looking at it. Which one of these would you say the mean is quite useful? Well, one or more of them. So, is the mean useful or not useful for number 1?
Useful.
Why? How many of the points are anywhere near the mean?
Well, like 6.
Not many, right? So what would be a useful range? Maybe we want everything relative. Look how many points are well away from the mean. So would we go with the mean is not particularly useful? You get that?
Yeah.
This one, if I draw the same circle, all the points are within it, okay? So the mean, I'm going with yes, useful. I'm happy to use the mean, all right? I'm not going to use the mean for this one. What about this one? Draw the same circle, and I would say the mean for this one is quite useful as well. These points, they're outside what we would want, but there's only a couple of them, yeah? And you now have a way. How could you justify not using them? Yeah, are they outliers or not? How can you determine if it's an outlier? 1.5 lots of the IQR added on. So you could actually, so can you see how everything's building up now? So you want to know, you've got a mean, the mean you've been able to do for years, but now you're looking at, well, does the mean actually represent the data well enough? You could say no for the first one, yes for the second one. For the third one, you're going, yes for most of it, but for a few points, it messes it up. What can I do to get rid of those ones? Are they outliers? So mathematically, can I forget about them? I can do a bit of calculation and go, yes, I can. It's not your opinion. Mathematically, you have decided they should not be considered. You have a reason, you have justification. Just like when people do statistical analysis, they say, well, I don't need to consider that person. He lives out in the sticks. He drives a three-wheel tractor. I don't need to consider him for whether he wants an office building built. So let's get rid of him out of the statistics. Do you understand that? There's someone that's well out of it. Let's not worry about him. And we can justify it. So this is why we're looking at our standard deviation. So standard deviation. So we've got, we would say, standard deviation is small for this one, standard deviation medium for this one. Okay? Potentially. And if I got rid of those points, what would happen to my standard deviation? Be smaller. Okay. Should we go through one example of doing the standard deviation? Because I've got another thing to ask you. So let's have a look at practice 1. Excuse me. On page 81. Practice 1, page 81 in the extended book. Okay. It says, for each set of data, find the mean and the standard deviation by hand, then with a calculator. Now, when it says with a calculator, do you remember I said yesterday we could do it on things called GDCs, the graphical calculators, that cost $200+. All right. So when it says by hand, it doesn't mean you're not allowed to use a normal calculator. You can still do that. All right. So let's have a look at this first set of data. So A, just a nice simple one to go through the process. 2, 2, 4, 4, 4, 5, 6, 6, 8, 9. Okay, so it says work out the mean and work out the standard deviation. So the mean, what is it?
5.
Well, what do we have to do? Add them up, divide by 10. 5? Happy with that? 3 lots of 4 is 12. That's 4. This is 12. So that's 24, 28. And then add a 9, 32, 40. Has something gone wrong? I've only got 49. Is it exactly 50? I must have added something wrong. So 50 divided by the 10 is 5. So the mean is 5. So now we've got to do the standard deviation. So this is long-winded, but we do have a formula. What's the formula?
Sigma. Standard deviation x equals square root, big one.
Yeah.
Sigma, and then the quantity of x line. X, you said it's called something, I forgot.
F,
Well,
x minus, let's do the one with the mean. That was the second one we did, didn't we? Yeah. Yeah. To the power of 2, all divided by the sum of the frequencies. Okay, so let's just go through what that means then. Well, what that means is we've got to do the sum of all the points subtracted from the mean. Okay, now the frequency comes from the fact that we have doubles and triples. So I am going to have to do this in stages, all right? So I'm going to do, the first point is
2.
a 2. Okay, I didn't mean to do that. Okay, first point is a 2, so I'm going to do 2 subtract 5 squared. Okay, and how many of them do I have? 2 of them. All right.
So we do the 2's together.
So you can do the 2's together. You notice I'm not going to do the rest. I'm going to now do, there are 3 lots of 4 minus 5 squared. There is 1 lot of 5. There are 2 lots of, there is 1 lot of 8, and there's 1 lot of 9. Okay, happy with that? Just taking each, so it's like doing every point separately. If every number was different, you'd have to do them all separately. There'd be no F frequency thing. Okay, so I've kind of just done, so far, I have only done this bit here. All right? I've not done any adding up yet. I'm still in the process of doing this bit. All right? So let's work all these things out. So what's 2 minus 5 squared? Can't believe you just got your calculator out. 9 times 2 is 18. 4 minus 5 is minus 1. Squared is 1 times 3 is 3. This is 0.
1? Oh.
So proud. This one is 1 squared, so this one's 2. 8 minus 5 is 3. 3 squared is 9. 9 minus 5 is 4. 4 squared is 16. Okay? What do I do next?
You add them up.
Add them up. So now I am going to do the next thing, which is add them up. So I'm going to add all those. And I get the answer
48.
48. I'm trusting you. I'm not doing it myself. 48. Okay. So then I'm going to do the next stage, which is to divide by the sum of the frequencies. So the sum of the frequencies is just how many numbers do I have. So what am I going to divide by? 10. Good. All right. So I'm going to divide by 10 and I get 4.8. Now I'm left with one final thing to do, which is square root. Okay. So let's do square root. So square root that. And I get
2.2. You're rounding to the
2.2 rounded to 1 decimal place. Okay. To 1 decimal place. Okay. So I've got the standard deviation as 2.2. Does that make sense? How to do it?
Yeah.
Yeah? Right. So before I get on with the next one, I'm going to ask you, is 2.2 a big, small, medium standard deviation?
Small.
Is it?
Because in comparison to the data set, it's in the smaller end
Is it?
of, I don't know.
Well, at least you're
Yes.
giving me a reason.
Yes, it is.
Yeah. So let's just compare again. The reason why up here, look, so I'm just going to rewrite the mean next to it, because what is the standard deviation for?
To see if the mean is reliable.
Yeah. And the larger what does a large standard deviation mean?
A larger spread of
Largest spread of the data. Yeah. Which means that the numbers are
Spread out.
further away.
Okay.
Yeah. So, what does 2.2 mean as a standard deviation when the mean is 5? If I had to say that as a sentence in English. I would say,
It's not
on average, all the numbers are 2.2 away from 5. Yeah? Does that seem like a large amount?
No.
No?
Why am I the only one saying? Oh! But since it's kind of like small numbers in the data set, 2.2 is like a large percentage of the range.
Done. 2.2 is a small number. Or is it? When you compare it to 5, being 2.2 away from 5 is quite a chunk, right? Now, of course, we've only got one data set. What do we really want to look at? We want to look at 2 data sets, comparing the same looking at boys and girls, for instance, and we need to know which one has a different standard deviation. But this is going to be my question. When is a standard deviation large or small? And it's got nothing to do with the actual number itself. All right? Yes?
What determines whether big or small is when it's compared to?
Yes. So 2.2, when you're comparing to 5, might be considered quite a large difference, yeah? But could a million be a large or small standard deviation?
Yeah, it could be wrong.
Could be both. Because, for instance, if I said to you, well, I'm looking at astronomical data, differences between stars, okay, and I'm looking at 1,000,000 kilometres from the mean distance away or whatever, is 1,000,000 kilometres when you're dealing with hundreds of light years a large or small number?
Tiny.
Tiny, tiny, tiny. So 1,000,000 kilometres when dealing with light years is tiny, right? But 2.2, when compared to 5, could be relatively large. Now again, that's up to your judgment, but I cannot say to you, this number is when standard deviation is big. It's not like, oh, if it's above 10, it's big. It's not. It's, as you guys have said quite correctly, it depends what the mean is that you're comparing to. If your mean is 5, 2.2 is quite large, maybe. If your mean is 500 and your standard deviation is 2.2, very small. Yeah, makes sense? Okay, I've done enough talking. I'll let you carry on with doing some more calculations for a bit.